Alright, what's up guys? In this video I'm going to pick up some differential equations, and we're going to be talking about second order non-homogeneous ordinary differential equations. And what we're going to try to do here in this particular problem is find the general solution to the second order non-homogeneous ODE using the method variation of parameters. Alright, so we're given this second order equation, 2y double prime plus 18y is equal to 6 tangent of 3t. And we want to use the variation of parameters. Now, there's another way that you can solve the second order non-homogeneous ODE, and that's by doing the method of undetermined coefficients, which I'll try to post a video on that at some other point. But variation of parameters is another way to do it. The only bad side about variation of parameters is that if you're not familiar with how to compute the Wronskian, and then that can be a bit of an issue. And when we're doing the variation of parameters, sometimes that can leave us with some really nasty integrals to deal with, so that makes it a little difficult. Whereas in with the method of undetermined coefficients, it's just a lot of messy algebra. So remember, to solve the non-homogeneous second order ODE, it's going to be a combination of our complementary solution and the particular solution, which will use the method variation of parameters. So we need to find the homogeneous solution here that'll give us our solution. So the first thing we need to do is divide by 2, because this is not in the correct form. So we'll do 2y double prime, we'll divide that by 2, we'll divide 18y by 2, and we'll divide 6 tangent of 3t by 2 as well to get it in the correct form. Okay, so if we do that, we'll get y double prime plus 9y is equal to 3 tangent of 3t. Okay. Now we need the homogeneous solution. Now remember that the form for the second order homogeneous ODE. So remember the form for that. The form is ay double prime plus by prime plus cy is equal to 0. If you don't know how to obtain the general solution or the complementary solution for the homogeneous part of the second order equation, I have videos on that specifically. So check those out, because if you don't know how to do that, you won't be able to get the solution to the non-homogeneous equation, because it's a combination. So our solution will be a combination of our complementary solution and our particular solution. Okay. Now what about variation of parameters? Okay. So again, we know that our second order non-homogeneous ODE, you can easily tell whether it's non-homogeneous by looking at what it's equal to. If it's equal to 0, it's homogeneous. If it's equal to some function, non-zero function g of x, then it's non-homogeneous. And again, we need to find the complementary solution, which is just the, we need to find our auxiliary equation and find the roots. And depending on what the roots are, the complementary solution to take a certain form, and then we'll need to pull a particular solution, which will use variation of parameters. When we get there, I'll talk more about variation of parameters, but let's just do the first part, and then we'll do the variation of parameters on the equation. Okay, so let's solve the homogeneous equation. So the first thing we need to do is we need to find the auxiliary equation, or the characteristic equation. So after we've done the simplification, we got y double prime, 9y. We need to set that equal to 0. Now we need the characteristic equation. So the characteristic equation in this case is going to be r squared plus 9r is equal to 0. Now we need the roots of this auxiliary equation. So what I'm going to do is I'm going to factor out an r. So if I factor an r out, I'll have r is equal to 0. And then I'll simply have r squared plus 9 is equal to 0. Okay, and if we find our roots here, we'll basically get complex roots, because r here is going to be equal to 3i comma negative 3i. Now since the solution to the homogeneous part contains complex roots, it will take a certain form, and we already know what that is. So please go back and check out my other videos on how to find homogeneous solution, because I don't want to go in it too much here because this is a bit of a long problem since we're doing variation of parameters. So our complementary solution in this case, well, I guess I can just remind you the form if we have complex roots. I guess I don't mind doing that. Okay, so if we have complex roots, then the complementary solution will take a certain form. It'll be C1 e raised to the lambda t multiplied by cosine of mu t plus C2 e raised to the lambda t multiplied by sine of mu t. Now C1 and C2 are arbitrary constants. So therefore, in our particular circumstance, our complementary solution will just end up being C1 cosine of 3t plus C2 sine of 3t. That is our complementary solution, or the solution to the homogeneous second order ODE. All right, so it looks like we've gotten the easy part out of the way. Now comes the variation of parameters. We'll come back to complementary solution a little bit. Let me get another sheet. Okay, so let's go ahead down here to variation of parameters. Okay, so basically all we have to do is just kind of use the formula. This W of y sub 1 comma y sub 2, that's the Wronskian. If you don't know how to compute the Wronskian, I got videos on that too. We'll identify what's going to be y sub 1 and y sub 2. It doesn't matter which is y sub 1, which is y sub 2. You're going to get the same answer regardless. And then we have our function g of t. So we just have to go back to our original equation to get the particular solution, and we'll do the Wronskian, and then the integrals again tend to get quite nasty, so that can be a bit of an issue for this method, but we'll deal with it when we get there. So let's identify y sub 1. Again, keep in mind it does not matter which one is y sub 1 and which one is y sub 2. It doesn't make a difference. So y sub 2 would just be sine of 3t. Now we need to compute the Wronskian. So let me remind you of the Wronskian. So for the Wronskian, in this particular circumstance, y sub 1, y sub 2, we're just going to have our matrix, and we're going to stick in our y sub 1 and our y sub 2, our functions. So y sub 1, y sub 2. We'll take the first derivative of both of those. So we'll get y prime sub 1 and then y prime sub 2, and we'll calculate the determinant, and that'll give us the Wronskian. That's kind of how that works. So in our particular circumstance, we'll have the following. I guess I'll do it like that. That way you don't mix up the one with the comma. All right, so let's go ahead and do that. So we get our matrix set up here. So we got cosine of 3t. We got sine of 3t. We'll take the derivative of both of those. The derivative of cosine of 3t, if you use the chain rule, it's going to be negative 3 sine of 3t, because the chain rule says I take the derivative of the outside, leave the inside alone, multiply by the derivative of the inside, and then the derivative of sine of 3t is 3 cosine of 3t. Now we'll calculate the determinant. So in that circumstance, we'll have cosine of 3t multiplied by 3 cosine of 3t. We'll subtract that from sine of 3t multiplied by negative 3 sine of 3t. Okay, now notice we got a common factor of 3, so this is just going to be 3 cosine squared of 3t plus 3 sine squared of 3t. Remember, cosine squared of 3t plus sine squared of 3t, it's just 1. So our Wronskien's just going to be 3. So we can say that the Wronskian, I think it's spelled Wronskian, right? Somebody correct me if I didn't. So the Wronskian here is going to be 3. So that's half of the problem here. Okay, so even with the Wronskian, that's not that hard to find, given you are familiar with how to find the Wronskian. Now we can do the variation of parameters, which involves us doing these somewhat nasty integrals. So let's move on to that. Okay. So we just got to sub everything in. So it's going to be yp of t. So we got to plug everything in. So what we'll have is negative cosine of 3t. Then we'll have our integral. And we'll follow the formula. So it'll be 3 times sine of 3t, or the integral of 3 times sine of 3t times tangent of 3t, all divided by 3 dt. I'm going to try to fit it in here. Hopefully it'll fit. Then we got plus sine of 3t. I'm going to try to write small. That way I can fit it in. And we just following the formula. That's all I'm doing. You need the variation of parameters formula. Some students are able to remember it, but if you can't, have it handy, and it's pretty straightforward at that point. And so then here, what we'll have is 3 cosine of 3t tangent of 3t, all divided by 3 dt. Now we're going to simplify all of this, but I just wanted you to at least get it set up that way. All right, so let's get another sheet. And you want to try, because the integrals can get quite nasty, so you want to try to simplify the integrals down as much as possible in order to save the headache. That's the only disadvantage of this particular method. So let's clean it up. So again, this would just be negative cosine of 3t. Our integral up there at the top, if you remember, it was 3 times sine of 3t times tangent of 3t all over 3. So we know that the 3's would cancel out. And so essentially what we'd end up with is the integral sine squared of 3t all over cosine of 3t. We're going to simplify that a little bit more too, but let's just get it in. And then the sine of 3t, which you got here. And then we'll have our integral here. And we're going to simplify this part as well. We can simplify this integral down to sine of 3t dt. Now, you do need to be familiar with your trig identities, because most of this stuff you're going to need to rewrite using trig identities, so make sure you have those on hand. All right, I'm not really at a point right now where I want to start integrating it, so let's just keep trying to clean it up. So we got negative cosine of 3t. Okay. Now remember, sine squared of 3t, I can write that as 1 minus cosine squared of 3t, because if you remember the trig identity from trigonometry, cosine squared of theta plus sine squared of theta is equal to 1. In our particular circumstance, if we have cosine squared of theta plus sine, or cosine squared of 3t sine squared of 3t, that's equal to 1. If we wanted to solve for the sine of 3t, it would be 1 minus cosine squared of 3t. So the integral here will be 1 minus cosine squared of 3t. Now, why do we need to change it that way? Because it makes the integral easier. And you'll see that once we actually go ahead and deal with it. And you'll see that it's actually not that bad at that point. Okay. And we've pretty much done all we can do on this other side. It's really nothing that can be done over here. Sine of 3t isn't hard to integrate at all anyway. All right, so now I'm pretty comfortable with go ahead and getting started with the integrals. we're not going to worry about these, the negative cosine of 3t and the sine of 3t. Those, we can think of them as constants. We're not worried about those right now. We'll worry about those at the end. Let's just deal with the integral right now. So we got 1 minus cosine squared of 3t all over cosine of 3t dt. So the best thing to do is to split this integral up. So I would split it up to the integral of 1 over cosine of 3t dt, and it's going to be minus the integral cosine of 3t dt. Now, although we did break these up, again, they're relatively easy to deal with, given that you are good with trig integrals. So remember, 1 over cosine of x is secant of x. So 1 over cosine of 3t is just going to be secant of 3t. So we'll have the integral secant of 3t dt. Okay. All right. In that particular circumstance, that's just going to give me 1/3 ln absolute value. Make sure you leave the absolute value bars up. And it's going to be tangent of 3t plus secant of 3t. So that's the answer for that. Because remember, we had the secant of t would be ln tangent of t plus secant of t plus c, technically. That's one that you have to memorize, and hopefully you know how to do that. It's just essentially just doing a u substitution, but you're not going to go through the whole process for that. Because that's pretty easy. And then we deal with the integral cosine of 3t dt. Okay, well, again, that's going to be 1/3 sine of 3t. Okay, technically plus c, but we're not going to add the plus c here. We don't need that for these types of problems. Okay, and if you do not integrate that, do a u substitution. But hopefully by the time you get to ODEs and you start learning about this type of stuff, you already know that one. Okay, so we've taken care of basically the left-hand side over here when we're using our method of variation of parameters. We'd have to clean it up a little bit, but we've taken care of pretty much the left side. Now the right-hand side, and when I say right-hand side, I'm referring to the side behind the plus sign. It's not bad either because we simplified that side down, which is this side over here. Okay. So we can go ahead and start putting everything together because we can integrate that basically in our heads. Okay, so remember the cosine of 3t that we have on the outside. I'm going to multiply by 1/3. So I'm going to bring the negative over, and then we'll have ln absolute value tangent of 3t plus secant of 3t. Make sure you leave your absolute value bars up. So we need those absolute value bars, and then that'll be minus our antiderivative. And again, I moved the 1 over 3 to the front, and basically kept the negative over on that side. So this would be sine of 3t. You can end up closing that up. And then we already know how to integrate sine of 3t dt. That's negative 1/3 cosine of 3t. So in a sense, this would just become sine of 3t all over 3 negative cosine of 3t. I just brought the 1/3 to the front. Okay. So we just need to kind of clean this up a little bit, and we'll pretty much be done in that circumstance. So cleaning everything up, we'll end up with yp of t is equal to negative cosine of 3t all over 3. Then we'll have ln absolute value tangent of 3t plus secant of 3t of all of that when we clean it up. And we're pretty much ready for our final answer. All we have to do is attach our complementary solution to the, or add our complementary solution and our particular solution, which would be the particular solution here after we clean it up. Okay, so the final answer here, y of t. I'm going to go down here because we're not going to have enough room. So let's go back to our homogeneous solution. So it's going to be C1 cosine of 3t plus C2 sine of 3t. And it'll be minus 1/3 because it's a negative there. And it'll be cosine of 3t ln absolute value. I just pulled the, I hate writing it like that, but you can write it like that, but you don't have to. You can pull the negative 1/3 out and just leave the cosine of 3t on top, because I have to technically just multiply in the numerator anyway. And then this will be tangent of 3t plus secant of 3t. And that is our solution to the non-homogeneous second order differential equation. So if your head is spinning right now, it's perfectly fine. I basically taught myself how to do this. We didn't cover it much in the differential equation class that I took when I was getting my physics degree. We touched on it a little bit in math methods, but not a whole bunch. And that's your answer. So that's how you do it. So let me know if you got questions. We can talk about it. But other than that, that is going to be it for us. See you next time.